All right, awesome. Okay, so I've got to now do in-person people and black box people, and one Loki holding Mjolnir in Captain America's shield. But for the most part, black box people. So hopefully the handwriting's better. New thing, but let's do this. So let's name this. What is the name of this? Hexane? Agreed. Well, my handwriting might be better, but my board management skills are still god awful. Uh, oh, this is good though. I can like pit the like online people against the in-person people. We can see who's more awake. Oh man, this is great. All right. Remember me. 2, 3, 3, 4. 3, 4. All right. Um, cool. Now let's draw a Newman projection from, oops, not for me, but from C3 to C4. So what I mean there is draw the Newman projection where you're going to look with my crappy, poorly artistic eyeball at carbon 3 to carbon 4. So the numbers that I give you, 3 to 4, so, right, so you name it, so that assigns each carbon a number, right? Now I can use those numbers to have you figure out where you should draw your Newman projection from, right? So, so let's draw the first one. So if carbon 3 is the front carbon, right? So what is on carbon 3? What are you going to see coming off of carbon 3? Two methyl groups I agree with, right? But what about, so that's this methyl, nope, sorry, this methyl and this methyl, right? But what about this group here? So you're going to see that whole thing coming off of it. So what is that? Isopropyl. So carbon 3 has two methyl groups and an isopropyl coming off of it. What are you going to see coming off of carbon 4? Another methyl group, right? So you're going to have this methyl group right here. You're going to have that. What's that? How many carbons is it? So ethyl. Oh, sorry, mask. Ethyl. And then what's left? What's the last thing coming off of carbon 4? I have a hydrogen, right? So I can see 3 bonds. All right, let's use this red one. 1, 2, 3 bonds coming off of that carbon, right? That fourth bond I can't see has to be a hydrogen. So here's one Newman projection. I'm going to redraw it real quick. I hope I remember it when I go to the next slide, right? So it was almost that, right? Did the same way I did. All right. So now that we have that first Newman projection, let's draw. Yes, ma'am.
I get asked here, how do you know where you start drawing your Newman projections?
Oh, you're you're always going to start drawing stuff staggered. I think it's just easier, and I don't care where you start. So you could have drawn this Newman projection to start with, but if you start with any staggered Newman projection and you draw all 6 going all the way around, you're going to draw all of them eventually. So it doesn't matter where you start. It just matters that you can then get to all of them. which is a challenge for making like a multiple choice matching test. Like, how do I make you pick the right one to start with so I don't have to grade it? All right, so now let's draw all the Newman projections we can for this molecule. Right, and the easy way to do that, I know this is a little ugly, is to leave the front carbon alone. So we can draw better here. Leave the front carbon alone, and picture that you're grabbing a group on the back carbon, and you're just twisting that bond between carbon 3 and carbon 4 a sixth of a turn. And you go from being staggered to being eclipsed. So now you're going to move the hydrogen over. The ethyl, it's kind of bad. That's a big eraser. The ethyl over, and then the methyl group will be over. So now they're all close together, they're eclipsed, right? If we keep turning, again, we'll leave the front alone. Why do I keep putting that so high? Leave the front alone. We'll turn another sixth of a turn. We'll get back to a staggered conformation. All right. Keep going, sixth of a turn. I'm definitely not going to get these all on one slide. He realizes too late in his example. All right. Sixth of a turn. So something you want to notice is that, like, in the starting structure, right, you can think that if you went like clockwise, starting at the hydrogen, it went hydrogen, ethyl, methyl on the back carbon, right? Each time I turn it, if you start at the hydrogen and go clockwise, it's still going to be hydrogen, ethyl, methyl. You never switch where your groups are. They should stay in the same relative orientation because it's a physical thing that you're like twisting. So like if I have my hands and I twist them and I twist my hand, it's still thumb, pointer finger, middle finger, right? And when I turn it, even though they're changing where they are, they're still thumb, pointer finger, middle finger. It doesn't like, you don't like start moving them around and stuff. I'm not throwing gang signs. All right. So then the last one, which I'm going to go to the next slide for, I'll redraw the last one on this page and then I'll try to remember the last one on that page. There we go. Great. One more twist gets me to this, 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 and that guy. And if I were to turn one more time and draw a seventh structure, that would get me all the way back to what I started with, right?
So I got asked right after I drew this why I drew a seventh structure, kind of what the point of that seventh structure was, and then I go on to explain it.
there are technically 6 structures. This seventh one is the thing I started with. So if I go all the way back a bunch of slides, right? So that last structure is this structure again. I just put it at the end to show you that you get back to what you started with, right? You went all the way around. But you don't have to draw that. Like if it's like draw all 6 Newman projections, you don't have to draw this one again because your starting structure is the one you already drew. Fair? Okay. Now we usually like write all this stuff out, but let's say we want to label all of the staggered conformations, right? there should be 3 staggered conformations and 3 eclipse conformations. Not counting like gauche or fully eclipsed, just staggered eclipse, like the simplest way to do it. So this would be staggered. This one would be staggered. This one would be staggered. These guys would be eclipsed. Right, and there's one eclipsed on the next page, which would be here. So we also should be able to label every gauche interaction, right? Should be able to show every gauche interaction. And a gauche interaction occurs when? When 2 non-hydrogen groups or 2 carbons are side by side. Yep. So any place you see two non-hydrogen groups side by side, there's a gauche interaction. So I use these little like parentheses that kind of overlap to kind of show that those 2 groups are banging into each other. Right, so there's a gauche interaction there. There's one here, and one there in that structure. There are never gauche interactions in eclipse structures. Gauche interactions are only in staggered structures. So you don't have to worry about labeling gauche interactions in eclipse structures because they don't exist. So this next staggered structure, one here, one here, one here, and one there. One here, one here, one here. There. So there are all of your gauche interactions. Reasonable? We'll abbreviate this. All right. So we should be able to name this, draw a Newman projection where you look at carbon 2 and have carbon 3 be the carbon in the back. And then you should then be able to draw every Newman projection. So sneakily, I basically taught you how to, if I give you any structure and I tell you what 2 carbons to look at, you should be able to draw any Newman projection of any compound I give you. Right? You would ethane, butane, anything. Not bad for like week 2. Right? You should feel very smart. All right, so what's the name? Okay, I will give you pentane. Isomethyl, not a thing. So pentane, we'll say that this is my longest chain because it has the most branches, right? Ethyl dimethyl, indeed, indubitably. Numbers. I have an answer. Okay. So why did I pick this chain as the longest chain as opposed to this chain? So one of the rules for picking your longest chain in like IUPAC naming is that you pick the chain that has the most substituents off of it, that has the most branching. So the green chain has 3 things coming off of it. The orange chain has 2, right? So for the official IUPAC name, you'd want to use the green chain. You could use the orange chain if you used isopropyl in your name, but since you could name it easily using the chain with the most substituents, you should use that chain. That make sense? Sure. So numbers. 3, 2, 4. Correctamundo. Both black boxes and real people. Good job. All right. So we know. So say molecule symmetrical makes it easy, but let's say we went this way: 1, 2, 3, 4, 5. So that means that I am going to be looking with my crappy eyeball that way, right? So that front carbon is going to be carbon 2, and the carbon behind it is going to be carbon 3, right? So we're going to pretend like this is all going to fit on this slide. What should you see on the front carbon on carbon 2? A methyl? Agreed. What else? A hydrogen. And it'd be 2 methyl groups, right? You see, so if this is carbon 2 right here, right? You're going to see both methyl groups that come off of it. You don't see the bond between carbon 2 and carbon 3 because that's the one that's blocked out, that you just know is there, but you can't see it. And then the other group you can't see is the hydrogen. So what's coming off of carbon 3? Ethyl? Isopropyl? And a hydrogen. There you go. Now, again, I've drawn it this way, but let's say you took the back and you like turned it a third of a turn and you had the hydrogen at the top and then ethyl isopropyl, or you switched them isopropyl ethyl. Doesn't matter, right? As long as you're starting with a Newman projection that has all the right things on carbon 2 and carbon 3, you're fine. You're going to get to the rest of the answers, the rest of the structures as you go around. So it doesn't matter where you start, as long as the thing you start with has all the right groups on it. All right, so we're going to try to remember how to draw this when we go to the next slide. Relatively confusing. How so? What are we confused about?
The comment was they were confused by everything, so I kind of tried to break down what the Newman projection was representing again.
So think of this circle as kind of that as carbon number 2, right? So think of that circle as carbon number 2, and then you're drawing the stuff that comes off of carbon number 2. So you're not drawing the bond between 2 and 3, but you're drawing everything else you see coming off of carbon 2. So you're like, I need to have a methyl, and a hydrogen coming off of carbon 2. And then you put that on carbon 2. And then you look at carbon 3 back here, right? You know carbon 3 is bonded to carbon 2, but you don't get to see that bond in the Newman projection. And then you're like, all right, what's stuck on carbon 3? And you say, okay, I've got an ethyl group, so I need to have an ethyl group, an isopropyl group, so I need to have an isopropyl group. Then I have that group you can't see, which is the hydrogen, which is the last group.
Here I got asked like kind of how you pick the order, like what group's on top, what group's on the left, what group's on the right, and I just kind of explained that it doesn't really matter.
Oh, like for putting my ethyl group at the top and then going around? It does not matter where you start. If you would have drawn, let me go to the next slide here so I can redraw it. If you would have drawn this, all right, carbon 2, the carbon in the front, still has 2 methyl groups and a hydrogen, right? So still the same thing. Carbon 3 in the back still has an isopropyl, an ethyl, and a hydrogen. It doesn't matter where they kind of start at the beginning as long as they're all there. So once they're all there, then you know you're going to see all the groups. So it doesn't matter where you start because you turn 360 degrees around that bond. So no matter where you start, you will get to all of the Newman projections. So then let's try to draw all of our Newman projections. So again, I think it's always easiest to leave the front carbon the same, right? So you kind of have something consistent structure to structure. So there's my front carbon. And I'm going to pretend like I'm grabbing that ethyl group and turning it 1/6 of a turn. Now, I like going clockwise, or yeah, clockwise. But if you're like, I want to go counterclockwise, don't care. As long as you end up with all of the structures, right? As long as you get there, I don't care how you got there. As long as you don't cheat, don't cheat. But other than that, we're going to make a little one here, see if we can get them all on the page. All right, so I'm going to keep turning. I'm going to grab that ethyl group again, turn it 1/6 of a turn. Keep going. Keep going. And eventually, you'll get all of your Newman projections. And they should always alternate staggered, eclipsed, staggered, eclipsed. That'll make it as easiest for you to follow as well, I think, because there's kind of a set pattern to it.
The question here was, what makes a Newman projection staggered?
Okay. So staggered is when you have, right, carbon or group on the back carbon, then you have group on the front carbon, then group on the back carbon, then group on the front carbon. So you alternate group on the back, group on the front, back, front, back, front. So when they're staggered, they're as far apart as they can be, right? As you can, I'm a little more animated now because I'm standing, right? They're like this. They're as far apart as possible. Eclipsed, they've moved on top of each other, right? So now they're as close as they can possibly be. So in all the eclipse structures, they're right in front of each other. So eclipsed, instead of being back front, they're right on top of each other. Yeah, so it goes, so it went, we look at top left, we have staggered, right? And then when you go 1/6 of a turn, you rotate into eclipsed. You keep turning, you go the next 1/6 of a turn, that gets you back to a staggered conformation, right? That is different than the first one. right? And then we're gonna go. I shouldn't go down that low. One second, I'm gonna go to the next slide real quick. So we were on. So what's bad is I'm keeping track of how I have to edit this in my head. So I'm like, oh, don't go clear to the bottom because I want to cut off the top if I can. And you're like, I don't care, old man. You need technology. All right, and then I go one more sixth of a turn, and I get back to an eclipse conformation. Great, so
So I got asked which one of these would be fully eclipsed or anti-staggered.
I don't ever have you worry about like anti-staggered or fully eclipsed unless it's in something simple like butane, because it becomes hard for you to like kind of figure out like fully eclipsed means like it's the highest energy conformation. And I don't expect you to be able to look at something that has like 5 or 6 different carbon groups and go like, oh, well, that one's clearly the highest energy. Like that's a bridge too far. So if it's something simple like butane or pentane where they just have 2 carbon groups, then it's really easy for you to say like, well, this is anti-staggered because the only 2 carbon groups are on opposite sides. Or this is fully eclipsed because the only 2 carbon groups are on top of each other. But when it becomes something where you have a lot of groups, I just want you to be able to pick out staggered and eclipsed and not worry about that like next step. Because like honestly, like I can give a pretty good guess at which one of these is highest in energy, but I might be wrong. So like I don't have that kind of like math brain in my head to like add up the numbers. So we go back, staggered, eclipsed, staggered. This is eclipsed again. This is staggered. So what I will, if you look at, if I had more space, right? If you looked at the old exams, it'll usually be like either a name or a structure, and then it'll be like name this or draw this. Then draw a Newman projection from here to here. Draw all the Newman projections. Then it'll say like label them, staggered or eclipsed. Then label the gauche interactions. Then blah 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 blah. So I'll like give you like a long. I would give you a laundry list of things to do. Still trying to work out how we're going to do this in a Moodle type environment, but I will work on giving you a laundry list of things to do. So yeah, I will tell you exactly what I want you to do. I'm not going to just be like Newman projection and you'd be like, I'm going to guess at what he wants. I would give you exactly what I want you to do. So kind of like I started here, but if there was a 4 and a 5 and a 6, right? This is the same one we ended the last page on. Right here, this is the last page. So then we get to the eclipse, which was green. Keep my color scheme.
So I got asked if the different staggered conformations of Newman projections for a molecule would always have the same number of gauche interactions in the different conformations.
So what do you mean gauche symbols be equal? Not always. So this one has 3, right? If I'm counting, right? This first one. So our gauche interactions. Right, so there's 3 there. This one has 1, 2, right? This one has, should have 3 again. So it's just depending on how many spots you have carbon beside carbon as to how many gauche interactions you have. So it's not always equal, right? The more carbon groups you have as substituents, the more gauche interactions you're going to have.
Some students commented they were having a hard time going from the structure to the Newman projection. So we just kind of talked through that here.
So, like, is the problem going from like structure, from that first structure to the Newman projection, and then after that you feel good, black box people? All right, so it's going from structure to that first projection. All right, so Not bad eyeball. All right, so let's draw a Newman projection from this carbon. We won't do all the Newman projections. Let's just draw that first one. See if we can get all on the same page here. So the circle that I draw, right? That's the carbon that you're looking at, right? So can I name it first? Oh, come on, man. Like, okay, 1, 2, 3, 4, 5, 6, 7. Heptane. So this is where I complained that at 3 o'clock in the morning, my smoke alarm went off. Like all of them in my house at the same time, and I was not on fire. So I was just up at 3 o'clock in the morning. I was very angry. I'm very sleepy now. Diethyl. Dimethyl. 1, 2, 3. Yep. So 3, 4, 3, 4. So 3, 4 diethyl, 3, 4 dimethyl heptane. So what's on that front carbon that I can see? So the first thing you want to note is the carbon that's behind it, right? You don't see this bond. Like that bond, you don't see it. So you're not worried about that as a group that's going to be sticking off because you can't see it. So what are the groups you can see that are coming off of that? 2 ethyls and a methyl.
So I got asked why there wasn't a hydrogen on the front carbon of the Newman projection.
So there are 4 bonds on this first carbon, right? So this first carbon right here has 4 bonds. So the 3 that you're drawing in, and then the one that has the blue X that you can't see. So then what's on the back carbon? There's an ethyl, there's a methyl and ethyl, and then what's the propyl? 1, 2, 3. Right. So you've got your methyl, your ethyl, and your propyl.
I got asked if it matters where you start your Newman projection.
Nope, doesn't matter where you put them to start with. Because if you go all the way around, you're going to get to all of them eventually. So as long as you gave me a Newman projection, even on the first carbon. So if you gave me a Newman projection that was that still works, right? That still front carbon has 2 ethyls and a methyl. Back carbon still has a methyl, and ethyl, and a propyl. Doesn't matter how they go on there initially, as long as they're all on there.
Even though we weren't going to go over the gauche interaction, someone asked me how many gauche interactions there would be for this molecule.
Yes, there'd be, for every staggered conformation, you would have 6 gauche interactions. Since this is a carbon on every thing, you'd have a gauche interaction here, 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 and there, right? Because there's no spot where there aren't 2 carbons side by side. Don't make me name this one. I'm going to bow to your bullying this time. Octopus person. All right. So, where'd that there? So we're going to look at that front carbon. right? What are the things that are going to be in the front carbon? Again, I'm not going to see the bond that I'm looking right down. That bond, not going to see it, not going to show up. Methyl ethyl hydrogen, right? We could even go crazy. We could like even draw the front like this. Doesn't matter. As long as you've got a methyl and ethyl and a hydrogen, you're good. Yes. How many bonds do you see on that front carbon? How many? Well, total, right? You see three. You see the methyl, the ethyl, and then that bond that you don't see in the Newman projection, right? So when you look at the skeletal structure, you're seeing three carbons come off of that front carbon. Carbons always make four bonds. So the fourth thing that you don't see is the hydrogen. So, right, you could just draw a hydrogen in there, right? Because you see one, two, three bonds coming off of that carbon, and then the hydrogen makes four. So you're always using hydrogen to fill in the spots that fill in the bonds that you don't see. So now what comes off the back carbon? So it'll be this carbon here. Ethyl and isopropyl and methyl. Like, I think it's pretty easy once you get the first structure drawn to work your way through all of them. It's just getting the point where you can draw that first structure and getting it to where you can go, okay, I see the card I'm looking at. What are the things I'm going to see sticking off of it? Yes, as long as all the groups are there, it does not matter what order you put them in. As long as they're all on there and they're all on the correct carbons. All that matters. So I wanted to circle back and do what was on carbon 4. We spent a little bit more time on this than I thought, but we'll do what was on carbon 4 and maybe do a couple chair conformations before we go. Right? So we talk about Newman projections. We're talking about rotating around that single bond. At room temp, single bonds freely rotate. Oh, handwriting get better. Right? So basically, any molecule at room temperature, its single bonds are going to be able to spin relatively easily. The reason for this is at room temperature, there's enough energy present to get over the barrier of rotation, right? So the barrier of rotation is the energy needed to go from one Newman projection, or to go from, say, staggered to eclipse, to make it cleaner like this slide. Right? So if you remember that graph we drew with all the energies of butane, right, where it would fully eclipsed was really high, then gauche, then staggered, then anti-staggered was really low. As long as there's enough energy present for you to get over the barriers between the two different, the staggered and the eclipse conformations, you're going to rotate freely around your bond. If there's not enough energy present, if that barrier is way too high, that barrier to rotation is too high, your molecule will get stuck in one conformation and won't move. Right? So at any time, if we were to think about a molecule at any time, right? If we were to take a picture of every butane in the world, right, they would be, you would have each possible conformation would be represented, right? You'd have some anti-staggered, you'd have some fully eclipsed, you'd have some gauches, and you'd have some eclipsed, right? But the ratio, how many of each is present, is based on the different energies. So molecules will spend most of their time in their low energy conformation. So butane will spend most of its time anti-staggered because that's the lowest energy, right? That's the easiest conformation for it to be in, right? The least number of butanes will be in the fully eclipsed conformation because that's the highest energy. That's the least stable conformation for it to be in. And so that's the one that is hardest for it to be in. So fewer of them will be in that conformation. So like if you have 100 butanes, like 95 of them or something will be uh, anti-eclipse or anti-staggered. You know, 3 will be um, the 3 will be words gauche, and then you might have 1 eclipsed and 1 fully eclipsed, right? But they're going to be the lowest energy conformations, or the ones that's going to be most populated, right? So we draw molecules. Yeah, all the letters in the words. So we draw molecules in an anti-staggered conformation just out of habit. If you look at a skeletal structure, right? If you were to look at, make this bond blue, the 2 carbons on either side of that blue bond are on opposite sides of the molecule from each other, right? They are as far apart as they can possibly be. That molecule is drawn in the anti-staggered conformation. So if you drew a Newman projection for every single bond, you would see that every single bond would be in this anti-staggered conformation as we draw it, right? And then they can move from there. But we always kind of default to drawing molecules in their most stable conformation. And it just feels easier when you actually draw them out. So far, so good? All right.
So I got asked what the point of Newman projections is. Why do we even do these?
What the Newman projections are showing you is every orientation of the groups between those 2 single bonds. So what they're showing you is how each of the groups on the carbons can be where they are relative to each other in space. And what you can do from this in simpler molecules is you can figure out which of those structures is lowest energy. So which one would be the one that if you were to look at a population of molecules, which one you'd expect to see the most. As they get more complicated, you're basically then just looking at how are all the different ways this molecule can behave. And then later on, we can use Newman projections and things related to it to be able to predict reactions, or what orientation are the atoms going to be in this product based on the Newman projections it can be in as the starting material. So you can use it as a predictive tool for reactions later on. But right now, you're just trying to see like how are these groups able to be relative to one another. This is a methyl group on a cyclohexane. What is the name of this conformation of cyclohexane? Chair. The chair conformation. Right? If you remember, you could see a little person laying on the chair reading a book with a little mask on. All right? Person on a chair. This methyl group, is that methyl group, what orientation is that methyl group in? There are two options when you're on a chair conformation. You can be blank or blank. This is an equatorial methyl group. Right, I'm going to jump over the slide. Oops. So now this methyl group, what orientation is that methyl group in? Axial. Right? Equatorial, the group points out, kind of horizontal, away from the ring. Equatorial, the molecule points straight down. Or sorry, the group points straight down. Which one's more stable? Which one of these two conformations that I have drawn is more stable? A or B? Which one's more stable? A. Right? And that's because that group that's equatorial points away from the other atoms in the molecule and doesn't interact with them. When a group is axial, it bangs into the other axial groups in the molecule, right, that are on the same side of the ring. So here, this methyl group can hit those two hydrogens, and there's a destabilizing interaction. So what is it called? Oh, it's supposed to change here. What is it called when these two groups bang into each other? What is the name of that interaction? I heard like 1-3, so I'm going to count it. A1-3. It's an A1-3 interaction, which means you're counting 1, 2, 3. The axial group on carbon 1 bangs into the axial group on carbon 3. So the A is for axial, and you're saying the axial group on 1 bangs into the axial group on 3. And then you do the same thing going the other way. This is also A13. The numbering for 1, 3 isn't like when you name. So you're basically counting 1, 2, 3 counterclockwise for the first A13, and then 1, 2, 3 clockwise for the other one. You're just saying that these two axial groups are 3 carbons apart, and they bang into each other. What is it called when you go from one chair conformation to the other? There was a term for that in the video. So the action of going from A to B, what is that called? Ring flip. So going from one chair conformation to another is a ring flip. And I think that's pretty much it for today. You can hopefully all do Newman projections like a boss. I gave you a little review on the video you watched, and we should be good. And right, and that should be where we started.
I gotta ask why the last structure had so many hydrogens on it.
Excuse me? Because I'm an idiot? He asked why the last one had so many hydrogens, and it's because I'm dumb. That's why. That's why. Don't do that on the test or anything. Be smarter than me. I've not put the bar high for you. I guess we're going to use the early classes lecture because that one had less screw ups. So sweet. That'll be the YouTube video. That's decided now. Close. 3 for ethyl and then 2, 3 dimethyl. Right? Because I'd start numbering down here. I'd go 1, 2, 3, 4. It would be 4. Good. See, not perfect. Oop, there we go. Sorry. I think I said 2-4. I think I did. I don't know. Whatever. I'm old. At 2:45 in the morning last night, my smoke alarm went off for literally no reason. Like all of them in my house all went off at the same time, and I had to figure out how to fix it. So I'm like sleeping. But I found out a baby will sleep through a smoke alarm. Can't really rely on him to save me in a fire. Like, okay, baby, you just gonna let me die? Cool.